We say a function is differentiable on a real interval if for every real number inside that interval, its derivative exists. So we're not going to go all the way back. I'm not going to define the derivative for you, but suppose you can take the derivative and it's well defined. That means it's a differentiable function. And informally, that looks like it's a smooth curve. Differentiable functions are nice and smooth, whereas a function that's not differentiable would have like something like this at places where it's not differentiable. Okay? So what if I want my function to be even nicer, even more smooth, even more well-behaved? We could require that my function is continuously differentiable. And continuously differentiable is just a word that means, a term that means, not only does the derivative exist, but the derivative function is continuous. And then beyond that, I could require that my function is twice differentiable, which means that the second derivative exists. It could also be twice continuously differentiable, which means the second derivative exists and it's continuous. And these things are building on each other, right? Like if it's twice continuously differentiable, that implies that it's twice differentiable. Twice differentiable implies that it's continuously differentiable. Continuously differentiable implies that it's differentiable, and differentiable implies that it is continuous to begin with. So this is just more and more layers of how nice a function can behave. So then we say a function is analytic. And the word analytic means that on some interval, it can be represented by a power series, like this, centered at the midpoint of the interval. That's the definition of the word analytic in math. So if I say sine is an analytic function, or cosine is an analytic function, or, 1 over x squared plus 1 is an analytic function, that means at least on some interval, I can represent that function with a power series. Most of the functions that we care about are analytic. This is most things, actually. They're at least analytic on some kind of interval. So like I said, differentiability implies continuity. If your function is differentiable, that means it's continuous as well. If you have a second derivative that exists, I already said this too, then the first derivative is continuous. Every infinitely differentiable function is infinitely continuously differentiable. So if I just say the words infinitely differentiable, I don't have to say separately that it's continuously differentiable because that's implied. You get this for free because infinitely differentiable means it's also differentiable to the next level too. And that means any analytic function is going to be infinitely differentiable. Sorry, maybe I misspoke. That doesn't directly imply this, but this is a separate idea. That every analytic function is infinitely differentiable because a power series is differentiable. If I wanted to take a derivative of a power series, like this one, I just use the derivative power rule. I bring down the k. This is now x minus c raised to the power k minus 1. And then I have to change one more thing. What should I change about this to make it correct? Well, I guess it is correct as it is, right? But what I could do is I could change that k equals 0 to k equals 1. It would be correct either way, I suppose, because if k is equal to 0, then the term is equal to 0, right? The first term would just be equal to 0. So it doesn't matter. Trick question. Now, every analytic function is infinitely differentiable because I can take a derivative of a power series and get another power series. I can take a derivative of that power series, and it just goes on and on forever. So analytic implies infinitely differentiable. There's another theorem you've seen before from Calculus 2. It's called Taylor's theorem. Taylor's theorem says, suppose f is a function that's n plus 1 times differentiable. So it's 5 times differentiable, or 6 times differentiable, or so on. Then, for some number in between c and x, this f function is equal to an nth degree Taylor polynomial plus a remainder. So we use capital P to represent the Taylor polynomial, and then capital R to represent the remainder. And you don't have to know this. I'm not going to quiz you on this. In fact, we're not even going to do the proof in here, because if you really want a proof of Taylor's theorem, you've got to kind of build up to it. And so that's something we would do in a real analysis course. But what I want you to know is that if I increase the lowercase n, right? So I increase my Taylor polynomial in degree. So it's the 5th degree Taylor polynomial, the 6th degree, the 7th degree, the 8th degree Taylor polynomial. Then I'm going to get a better and better approximation of my function. Because 2 reasons. I should say maybe 1 reason is this. In the denominator here of this remainder, I've got n plus 1 factorial. And so as n increases, this remainder is going to decrease. So that means the Taylor polynomial itself is getting closer to the function. And this is technically only a theorem that applies to an n plus 1 times differentiable function. But if your function is analytic, meaning it's infinitely differentiable, or even if you just say it's an infinitely differentiable function, then we could make these Taylor polynomials be arbitrarily large in degree, and then if I take the limit as n approaches infinity, the Taylor polynomial converges to the function itself. And we call this a Taylor series. That's the definition of Taylor series. So Taylor's theorem is difficult to prove, right? Not going to do that in this class. But the point of Taylor's theorem, what it's kind of leading us up to, is this idea that if you have an infinitely differentiable function, and you want to take the limit of your Taylor polynomial sequence as n approaches infinity, then you'd get this. And in the limit, it's actually equal to the function you're trying to approximate. If a Taylor series is centered at 0, then we call it a Maclaurin series. And this is something that you should know. So this works for every infinitely differentiable function. And if I have an infinitely differentiable function, that means I can represent it by its Taylor series. And a Taylor series is a power series. And so that implies that every infinitely differentiable function is analytic. So the word analytic is synonymous with infinitely differentiable, because that relationship goes both ways. Okay. There's another word I want you to be familiar with, and the word is asymptotic. So if I were to say, the following formula is true asymptotically as n approaches infinity, what that means is that the formula itself is never actually true as long as n is equal to some finite value, like n is equal to 1,000, n is equal to 1,000,000. But it is true in the limit as n approaches infinity. A lot of the formulas you use in statistics, if you've taken a statistics class before, a lot of those formulas are actually coming from asymptotic evaluations. The formulas are not true themselves, but in the limit as your sample size approaches infinity, they become valid. And so that's why we normally say in statistics, make sure you have a sample size greater than 30 or something like that, so that the formulas become approximately true. So exercise 2, look at that function. Big ugly rational function. Prove that this function is asymptotically equivalent to 1/2 x minus 3/2 as x approaches infinity. Maybe you've seen this before. Maybe in like a pre-cal class you've seen this. But I'll show you if you haven't, if you don't remember this. What I'm going to do is I'm going to rewrite my f of x function. And what I would like to do is take every single term in both the numerator and denominator, and I want to divide by x squared, okay? And if I do the same thing to the top and the bottom, then it does not change the value of the function, right? If I divide the numerator by x squared and I divide the denominator by x squared, then I haven't actually changed the value of the function, I'm just changing the way that it looks. And so I'll get x minus 3 minus 500 over x plus 9,999 divided by x squared divided by 2 plus 75 over x minus 1,000,000 divided by x squared. So now, let x approach infinity. As x becomes a really, really, really big number, like x is the number, a trillion. Say x is a trillion. Well, this term matters a whole lot because it's a trillion minus 3. But what about minus 500 divided by a trillion? That's less than a billionth, right? It's less than 0.0000001. And what about this? It's like 10,000 divided by what's a trillion squared, a huge number. And if that's a huge number, then this is practically 0. These become negligible terms as x becomes really large because they're divided by a super, super duper huge number. And so in the limit, as x approaches infinity, we've got x minus 3 over 2. And this is the only part that matters asymptotically. So I would say asymptotically, this function is equivalent to 1/2 x minus 3/2. Is it clear how we use this word, this adjective? Okay. I'm just going to graph it because it doesn't take that long. We've got x cubed minus 3x squared minus 500x plus 9,999 over 2x squared plus 75x. What is it? Minus a million. And I said, you know, asymptotically this is equal to 0.5x minus 1.5. So in blue, that should be the asymptote. And to see it, we just need to zoom out far enough. And now you can see if I let x become a really large number, then the red curve, my original function, becomes equivalent to the blue line if I just go far enough out. So the deal with asymptotic evaluations is that, like, when you're far away from the limit, it could look radically different. Like this red curve looks radically different from the blue line. It's only true if you get a large enough value of x. Okay, next. Who has seen big O notation before? Great. Is that a computer science thing? Good, 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 good. So y'all are familiar. And for the rest of you, this is big O notation. We would want to use big O notation if we want to cut through a bunch of, noise might be the best way to put it. It's like if there's a bunch of stuff that doesn't matter to us and we want to quickly just say what matters, what's the core of our intention here, sometimes big O notation can help. So we're going to write a big capital O, right, the one right here, and then in parentheses, we're going to write the thing, the variable, and whatever function of the variable it might be, that the remaining terms are asymptotically proportional to. Like, in my example, we could write the Maclaurin series for sine, and the Maclaurin series for sine is x minus 1 over 6x cubed plus 1 over 120x to the fifth minus 1 over 5,040x to the seventh plus blah, blah, blah. And you can keep going forever. But the thing is that if what I'm really concerned about, if we just want an approximation for sine near the point x equals 0, near the point x equals 0, each one of these continuing on terms matters less and less and less and less and less. Because if x is a small number, close to 0, then x to the 7th power is smaller than x to the 5th power, and x to the 9th power is even smaller than that, and x to the 11th power is even smaller than that. So I don't really care about the terms after a certain point. And so instead, I think the variable we care about is x, and the fastest, or maybe I should say slowest growing function of x in this case, the slowest growing function of x and all the remaining terms is x to the 5th power. So I use this big O notation to say, you know, the remaining terms, they're asymptotically proportional to x to the 5th. And we forget about the rest of it. So in this context, we're saying that this part before the big O notation is a good approximation near x equals 0. If I wanted to include another term in my approximation, then I would use big O x to the 7th power, because that's the next slowest growing function of x, and so on. Another thing we don't include is we don't include constants in big O notation. We don't care about constants. And so even though the x to the 5th term was 1 divided by 120 x to the 5th, I'm not going to put 1 divided by 100 x to the 5th. I'm only going to put x to the 5th. So we neglect to write the constants. Pivoting topics again, I want to show you how to divide power series just in case you haven't done this before. And what this is telling me is I know tangent of x is equal to sine divided by cosine. And I know the power series for sine, the Maclaurin series for sine, looks something like x minus 1/6 x cubed plus 1 over 120 x to the 5th, and so on. I know the Maclaurin series for sine looks like 1 minus 1/2 x squared plus 1 over 24 x to the 4th plus minus 1 over 720 x to the 6th, and so on. So how do I actually get the power series, the Maclaurin series for tangent? This is what we're going to do. We're going to draw kind of a, I don't know what you call that, kind of a box thing. And if this is true, I could write that sine of x is equal to cosine times tangent, right? Just multiply both sides by cosine. And so I'm going to write the cosine then on this side of my orange box. I'm going to write 1 minus 1/2 x squared plus 1 over 24 x to the 4th. And then my answer for the tangent series is going to be up on top. What goes inside this grid is going to be the sine series. And what I know for the constant in the sine series is it's 0. The constant term in the Maclaurin series for sine is 0, right? So I'm going to put a 0 in that first box. And then I think, what times 1 gives me 0? 0, okay? Then I also have 0 times negative 1/2 x squared. That's also 0. But here's the next part here is I have to come up with something. Well, hold on. I'm not being very careful, am I? I need to space these out a little bit more. The problem is what I really should do is I should create a new row for every power of x. But what I wrote down for cosine, I was skipping over the odd powers. I was skipping over the odd powers. So here's like 0x, and then here's minus 1/2 x squared, and here's 0x cubed, and here's plus the 1 over 24x to the 4th. Okay, that's better. So 0 times 0x is 0. 0 times everything is 0. Now I'm thinking to myself, these boxes here. Oh, I hate that. It won't even let me undo. Undo. This highlighter is terrible. Okay, these two boxes have to add together to be equal to this. 1x, okay? So that means 0 plus 1x has to be equal to x. And that means this has to be 1x, so that 1 times 1x is 1x. Okay. Now, for sine, the x squared term in the sine Maclaurin series is 0x squared, right? There's not an x squared term in the sine Maclaurin series. So these three boxes that I shaded yellow need to add together to be 0x squared. And if this is 0x squared and this is 0x times 1x, so it's 0x squared, then this is 1 times what? And what does this need to be? It still needs to be 0x squared, so that means this must be 0x squared. Okay. Next term in the sine series. Dividing power series is kind of a slow, careful process if you haven't already picked this up. We're going to have this, where these 4 boxes in my grid need to add together to give me the negative 1/6 x cubed. So I can fill in most of these by multiplying, right? This would be negative 1/2 x cubed. And this would be 0x cubed. And this would be 1 times something. But what I need all of these blue boxes to add up to is negative 1/6 x cubed. So if I've got a negative 1/2 x cubed and I only want a negative 1/6 x cubed, what should this be? What's the thing that goes in the blank cell right here?
1/3.
Yes, good. It should be positive 1/3 x cubed. And so what should I write up above here?
1/3 x cubed.
Yeah, it should be the same thing because it's multiplying times 1. So that is to say that, like, what I'm trying to construct is something where cosine is the left side of the box and tangent is the top side of the box. And I want cosine times tangent to give me sine. So sine will be the area of the box with side lengths, cosine, and tangent. And so every single step along the way, there's a little bit of investigating that you have to do. But at least we know that for my tangent power series, the first 2 non-zero terms are x plus 1/3 x cubed. And if you want more terms of tangent, you have to continue this process on and on and on. Okay, we're going to use that later, but it's possible to divide 2 power series. This is the main point of what we're talking about today now. If we have a root finding method, like the bisection method, the secant method, Newton's method, etc., we are going to define the order of convergence and the rate of convergence according to a scaling law formula. And this is the scaling law formula. What the scaling law formula says is that the absolute error at iteration n is approximately proportional to the absolute error of the previous step raised to some power. That power is called the order of convergence. The k constant that makes it proportional is called the rate of convergence. That has to be a constant, so it doesn't change from one iteration to the next. And what else? This little wavy sign is telling you that this is true asymptotically as n approaches infinity. So this is never exactly true. This scaling law formula is never exactly true. If it was exactly true, then you would get this weird situation where you could like repeat Newton's method like 3 times, and then you could use the scaling law formula to solve for the exact value because you know what the errors should be. But it's not. It's not exactly true. This is only asymptotically true because there's going to be some higher order terms that we neglect and forget about. We use the big O notation and then we push them out the door in order to come up with these scaling law formulas. And so this is not exactly true, and that's the reason we need sort of numerical methods. If this were exactly true, there'd be no need for numerical methods, but this is true asymptotically. So here's a question. Would a better root finding method have a high order of convergence or a low order of convergence? If you have a good method, should the lowercase p be a large number or a small number?
Smaller.
Why do you say that?
Because the greater p is, then the greater the error p.
It depends, right? If your absolute error is like the number 2, then a large p would give you a larger number, right? But what if your error is the number 0.1? Then a large p would give you a smaller number. And the assumption here is that we're doing this asymptotically. So after you've done a few iterations of your method, then this becomes true. And you hope that after you do a few iterations of your method that the error is small, less than 1. You hope that the error is less than 1 by the time the scaling law formula becomes true. And if the error is less than 1, then do we want the order of convergence to be big or little? Yeah, big order of convergence is better. Would a better root finding method have a higher or lower rate of convergence? That's right. Which one do you think matters more? Your order of convergence or your rate of convergence?
Order.
Yeah. Yeah. You can tell by the title of my lecture notes and homework that order of convergence matters. Certainly more than rate. And the reason is like maybe your rate of convergence is better in one method. Let's say method A has a rate of convergence that's only 100th of the rate of convergence of the method B. So A is better if you only look at rate of convergence. But as soon as you've got a difference in the order of convergence and your absolute error becomes small, like on the order of 0.01, well, now suddenly it doesn't matter what the rate of convergence was because the higher order of convergence is going to accelerate method B. I don't know if that makes sense. But order matters. Rate doesn't really matter. We're going to figure out what these orders of convergence are by trying to take our formulas that we have for the Newton's method and the secant method, and then we're going to just like beat them up and shape them into a form that looks like a scaling law, and then we're going to compare their exponents. Okay? Okay. So let's talk about it. We'll do bisection method first, I guess. Exercise 5 says, state and prove the order of convergence for the bisection method. Well, the order of convergence for the bisection method is 1. That's something you should know. And the idea is this. Every time I do an iteration of the bisection method, I cut the interval in half. The width of the interval, or more specifically like half the width of the interval, the distance from the midpoint, which is your best estimate, out to the edge of the interval, that's the maximum possible error. So every time I repeat an iteration, I'm cutting the maximum possible error in half. So I could say something like this. The maximum possible absolute error in iteration n is 1/2 of the maximum possible absolute error in the previous iteration. And it's not true for the absolute errors because we don't actually know what the root is, but it is true for the maximum possible error, absolute error. And so if I compare that with the scaling law formula, do you see how the rate of convergence is 1/2 and the order of convergence is 1? Okay, so the order of convergence for the bisection method is 1. Now we're going to state the order of convergence for Newton's method. And for Newton's method, the order of convergence is 2. The sketch of a proof. What do I mean by sketch of a proof? A sketch of a proof is like a set of instructions that you might want someone else to follow if they were going to actually sit down and write out all the details of the proof. And the sketch of the proof is this. Number 1, rewrite the Newton's method formula in terms of the absolute error, or maybe I should say actual error. I'll show you how to do that in a minute. Step number 2, express the function and its derivative in terms of their Taylor series. So we're assuming that these are analytic functions, right? Centered at the root that we're trying to find. Number 3, we're going to perform power series division. We don't have to do a bunch of terms from power series division, but we'll do like 2, maybe 3 terms of power series division. And then number 4, we are going to, let me think about what happens in that proof after you do power series division. You would, I know you're pretty darn close to the answer at that point. Maybe there's just some like simplifying you have to do. And then compare your result with the scaling law formula. So that's why I said, we're going to take the Newton method formula and we're going to beat it up and reshape it until it looks like a scaling law formula. That's kind of the 4-step process that we're going to follow. So this is not a proof, right? A sketch of a proof is just kind of like a skeleton. It's an outline. If somebody asks you for a sketch of a proof, just give them an outline for what kind of steps the proof is going to follow to get the right answer. So let's actually do it. State and prove the order of convergence for Newton's method. The order of convergence for Newton's method is 2. We're going to start our proof by restating the Newton's method in terms of the actual error. And so that's x is my current estimate minus r, which is the actual true value of the root. That's what my epsilon is going to be. Okay, this is the Newton's method formula. This is what you have memorized for it, right? What am I doing between the Newton method formula and this next step? What's happening here? Yeah, we subtract r from both sides. All right, what happens in the next step? What happens right here?
You just rewrite it in terms of error.
Yep. We just use that to make a substitution. Okay, now we're going to consider the Taylor series of my function centered at r. And so now I've written out what a Taylor series of my function looks like. Tell me what is happening in this step.
Just substituting the e for x minus r.
Yep. The same thing, we're going to substitute the x minus r for this epsilon. Also notice this. What happens here? Do you notice how I have an f of r right here, but I don't include it in the next line? What happened to it?
It disappeared.
Why did it disappear?
Is it because it's irrelevant?
It's not irrelevant. That is the first constant term of the Taylor series when you write out a Taylor series centered at r. What is the definition of my lowercase r?
Center r set 0.
Yeah, r is the 0 of the function we are trying to find using Newton's method. And so that means the function at r has a value of 0. So that's why I'm not including it in the next step. Okay. From here to here, what have we done?
Use the big O.
Yeah. So instead of writing plus dot 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 to represent infinitely many terms after this, I'm using my big O notation to keep everything short and simple and say, listen, I'm only really concerned about what happens when epsilon is small, when epsilon is near 0. And that means every additional term of this Taylor series gets more and more meaningless to me because I have larger and larger powers of epsilon, and epsilon is near 0. And so those terms, I can neglect them. The most important term is going to be this term with an epsilon cube. And when I use big O notation, I make sure I keep track of my variable and what the function of the variable is, like epsilon cube, but I neglect the constants. I don't care what the constants are. Okay, so asymptotically, all the other terms are going to be proportional to epsilon cube. All right, so now we consider the Taylor series of the derivative, which means I'm going to start from here and then take the derivative with respect to x. And I get this series. Now, what happens from here to here? Epsilon equals x minus r, right? Make that substitution. And then from here to here, we just wrap things up nice together using the big O notation. Because all of the other terms in this Taylor series are going to be asymptotically proportional to epsilon squared. Okay, so we had a formula back here. We are going to revive this formula again, but I'm going to replace this f of x in the numerator and the f prime of x in the denominator with their Taylor series that we just found, okay? And there we go. That's what it looks like if I replace the f function in the numerator and the f prime function in the denominator with their Taylor series centered at r. So what happens between this step and this step?
You're minuscule negative epsilon.
I'm going to factor epsilon in out of the numerator. So you see all the terms in the numerator went down by 1 power of epsilon, and I factored that out. Okay. Next step, from here to here, what is happening?
Divide the top and bottom by f derivative.
Mm-hmm. I divided every single term in the numerator and denominator by f prime of r. Okay. Now, what happens? Oh, I already told you. We're going to use power series division now. And using power series division, I can divide the power series in the numerator by the power series in the denominator, and this is what I get after power series division. Okay, what happens right here in this step? I see a typo too. Tell me what happens and then tell me what my typo is.
You should figure the epsilon, but I forgot the square.
Yeah. So what's supposed to happen in this step is distribute the epsilon and then notice that epsilon minus epsilon is equal to 0. So that's going to cancel with the 1 here. And then the typo that I need to go back and fix later is that that should be squared. I'm going to distribute the epsilon. Asymptotically, as this epsilon approaches 0, we can ignore the rest in the big O notation because the stuff in the big O notation, all of the other terms of that power series, are asymptotically proportional to epsilon cube. And epsilon cube is going to shrink faster than epsilon squared does when epsilon approaches 0. And so ignoring that, we get this. And after we ignore the rest, we're going to end up with something like this. And then remember our scaling law, how we define the order of convergence here with my scaling law. Compare these two, right? Compare this equation with this equation. On the left side, I both have the absolute value of epsilon n plus 1 equals, on the right side, I've got 1/2, some constant that's the absolute value of the ratio of the derivatives, blah, blah, blah. And then the absolute value of epsilon n raised to the power 2 raised to the power p. So we say p is equal to 2, and the k must be equal to that constant. So this gives me, by comparing it against the scaling law, both the rate of convergence and the order of convergence. But we don't really care what the rate of convergence is. What we mostly care about is what is that order of convergence. So again, that's what I meant to say whenever I said you take the Newton's method formula, you kind of beat it up a little bit, and then try to make it look like the scaling law formula. Now that it looks like the scaling law formula, you can read off what the order of convergence is. And the k part, I want you to just recognize this. Even though I've got f double prime and f prime of r, that's still constant because we don't know what the lowercase r is, but that's a fixed point on my function. And so that will never change. That k doesn't change from one iteration to the next. Anyways, questions about that? No? Cool, so moving on. State the order of convergence for the secant method, then provide a sketch of the proof. The order of convergence for the secant method is 1 plus the square root of 5 divided by 2, which is like 1.6-ish. So like I told you a long time ago, the secant method is considered to be faster than the bisection method with an order of 1, but not as fast as the Newton method with an order of 2. It's like 1.6-ish, kind of in the middle. But isn't it nice that we can actually put a numeric value to how quick it is? The sketch of the proof is exactly the same, by the way. Number 1, start with the formula for the secant method formula. Number 2, express it in terms of the actual errors, not just the x values. Number 3, we're going to need Taylor series of the function evaluated at the nth iteration and the n-1 iteration centered at r. Number 4, after we get those Taylor series, we're going to plug the Taylor series back in to the formula we got from step 2. And then we are going to simplify that as much as we possibly can. There's going to be a factor that we factor out to make it nice. And then we can use power series division. And when we were done with power series division in the Newton's method case, we were like 99% of the way there. But in the secant method case, we're not there yet. We have to do some bad college algebra, voodoo witchcraft involving the quadratic formula. And it is kind of a trick to follow, but we will eventually get to the answer. But it looks pretty much the same. Like the steps are the same. You start with the formula, you express it in terms of the actual error, you use the Taylor series. This time with the secant method, we don't need the Taylor series of the derivative though, because that doesn't appear in the secant method formula. And then we simplify, and then we do power series division, and then after that you're close, but there's still an additional trick if you're dealing with the secant method. So let's jump into it. Start by restating the secant method in terms of epsilon. So, first step, what do? We subtract r from both sides. The second step is related to this stuff in the parentheses. Do you see the stuff in the top right corner here, xn minus xn minus 1? I can rewrite that as epsilon n minus epsilon n minus 1. Because here in the middle where I have xn minus r, and then I have two negatives, well, two negatives make a positive, so I'm really adding that r back there, keeping it all balanced. So then we whip out our Taylor series for my function f. And we do the same thing, plugging in xn and xn minus 1. And then we subtract these two. Because this minus this equals this. This is another tricky trick. There's lots of little tricks here. But what's happening in this step with the purple arrow next to it? Yes, I'm factoring out epsilon n minus epsilon n minus 1. And that's easy to do for the first term that just has f prime of r. But the second term that has epsilon n squared minus epsilon n minus 1 squared, do you see how if I multiply this factor times this factor, I'm going to get that factor? Okay, so it's a little tricky. Okay. So we take the formula we had before for the secant method in terms of the epsilons, and we are going to plug everything in, everything possible. So we're going back here, grabbing this, but the difference is that I've replaced the denominator with this, right? That's the denominator now. And what's great about this is notice, well, I'll ask you a question. What happens in this step? Yep, there's a factor that I cancel out in the numerator and denominator. It's the factor that looks like that appears in the numerator and denominator. Okay, that's better. Now we also have an f of x. We can replace that with a Taylor series, and that's what we do. So take this guy in the numerator, it gets to become a Taylor series, and we have our next iteration of our formula. The next step should look familiar to you. What's happening here? Yep, and I see another typo. I think this is supposed to be a 3. But yeah, we're going to factor out an epsilon from the numerator. Again, this should look familiar to you from the Newton method proof. What's happening here in the purple step? Yep, divide top and bottom by f prime of r. Then, like we did before, we're going to use the power series division to go from here to here. And the next step is going to be a matter of distributing the epsilon. And then canceling out a positive epsilon with a negative epsilon. 2 negatives make a positive, and then there we go. Now, if I put absolute values on the left side and the right side, this is what I get. And, you know, it almost looks like a scaling law formula. Because in our idealized scaling law formula, I've got the absolute value of epsilon n plus 1 equals some constant times absolute value of n plus 1 epsilon, sorry, I got tongue-tied. The absolute value of epsilon subscript n raised to some power. The problem here is that now we have this additional factor, right? That epsilon with an n minus 1. That's a problem. And it's keeping us from having a perfect scaling law formula. So remember, we want a scaling law formula that looks just like this. And if I shift the indices, this is true as well. What the heck is going on here? What's going on here in this green step is I'm taking this definition of the absolute value of epsilon subscript n, and plugging it in here. So that way I should have the absolute value of epsilon n plus 1 is equal to k times this. On the right-hand side of the middle equation, it's k times epsilon n minus 1 raised to the power b raised to the power b. So now we distribute the p and we get k times k to the p times the absolute value of epsilon n minus 1 raised to the power p raised to the power p. And if I'm sequentially taking this and raising it to the power p and then again raising it to the power p, there's a property of exponents that says I could just raise that to the power p times p, aka p squared. And then k times k to the power p is going to become k raised to the power p plus 1. And that is pretty good. We're not totally done yet, but that's pretty good. When it says compare this to our previous result, the previous result we're talking about is comparing this one with this one. And we're going to take these ones I've circled in orange and set the right sides of these two equations. Set those equal to each other, and this is what you would get, right? So in this new equation, I've got the right side of that, boop, equal to the right side of that, boop. And our goal here, when you look at that, is to solve for p. Well, this absolute value of epsilon n minus 1 times absolute value of epsilon n minus 1 raised to the power p, that's going to become absolute value of epsilon n minus 1 raised to the power p plus 1. I can divide both sides by k, and that kp plus 1 just becomes kp on the left side. And we'll say, this is my constant, this is my constant. And then over here, this is the part where I have an absolute value of an epsilon raised to some power. And so that means the p squared has to be equal to p plus 1, because there's a p squared on the left side of the equation, there's a p plus 1 on the right side of the equation. You still feel good about that? So now to solve for the order of convergence, to solve for p, this is a quadratic equation. P squared equals p plus 1. This is p squared minus p minus 1 equals 0. And so now use the quadratic formula. P equals negative b over 2a plus or minus the square root of b squared minus 4ac divided by 2a, where a is 1, b is negative 1, c is negative 1. Do that and simplify, and this is what you get. So that's the order of convergence for the secant method. It's wild. Whoever came up with that the first time. So let's talk about Regula-Falsi method. If the Regula-Falsi method were to, you know how it's just the secant method formula, but you force it to shrink the interval. You don't allow it to go outside of the interval, right? You only allow it to shrink the interval. So if A and B alternate, which one gets replaced? In that case, then the Regula-Falsi method is identical to the secant method, and its order of convergence then is 1.6-ish, right? Just like the secant method. But if only A or only B are replaced, like in the case where there's a constant plus or minus sign on the concavity of the function, then in that case the order of convergence goes down to 1. And a lot of times the rate of convergence will be greater than a half, and so in that case it's worse than the bisection method. But it's hard to deal in absolutes here and say one is definitely better than the other, because that's just not true. There's situational cases where one's better than the other here and worse than the other there. But it depends, right? Order of convergence for the Regula-Falsi method is between 1 and 1.6. And you can't really say much else about it because it's either acting like the bisection method or acting like the secant method. Discuss the order of convergence of the Newton bisection method. Well, if the Newton formula is used for a step, then it has the same order of convergence as Newton's method. But obviously, if the bisection midpoint is used for a step, then the order of convergence is just 1, right? Just like Newton or bisection. So for that kind of mixed up safe method, you get somewhere between 1 and 2. And here's what I want to say last. On your next test, I might ask you a question like this, but on the last column, instead of asking you, is the method fast, we're going to be a little bit more specific. And I'll ask you instead, what is the order of convergence? And then you would say something like this. Regula-Falsi is between 1 and 1.6. And Newton bisection is between 1 and 2.